Hello, fifth graders. This is the video where we officially, formally learn about adding or subtracting two fractions with different denominators. I'm actually not going to show examples of subtraction just yet. It's not that it's difficult. It's extremely similar to the addition of fractions, but I have a little bit of groundwork that I'd like to lay before we officially look at subtraction. I'll show you how you can do them and get the answer, but as far as the explanation, that's going to wait a little bit. Let's look at the top of the board here for the two formulas for adding and subtracting two fractions which have the same denominator. Those letters up there, A, B, and C, as it says, stand for whole numbers. The whole numbers are 0, 1, 2, 3, 4, 5, 6, the numbers that we deal with when we're very young. The only restriction is that the C cannot be 0. You can never have 0 in the denominator of a fraction. This is a fundamental law of mathematics that I will explain to you in the future. I already have a video, and I'll present it to you at some point explaining why the denominator can never be 0. For now, let's just accept that. Of course, a fraction is indicated with a fraction bar and then a numerator on top, denominator on the bottom. The denominator indicates how many equally sized pieces the unit has been divided into, and the numerator simply keeps track of which one it is from 0, just sort of counts them. The word numerator kind of looks like number in the sense that just counting the fifths or counting the halves, whatever might be indicated by the denominator. So we can simply say about adding and subtracting fractions, the fundamental rule that all people around your age learn is we never add the denominators or subtract the denominators. So there are the formulas. I like to introduce general formulas using letters as soon as possible to fifth graders. Here we have a fraction A over C plus B over C. Notice the denominators are the same. The denominator of the answer or the sum will be C as well. And then we simply add the numerators. The only difference with subtraction is we subtract the numerators and keep that same denominator. So, before we do a few additions of fractions, I'd like to lay some groundwork which will be valuable for us going forward when we get into negative numbers. And this is a little bit of a sophisticated concept for fifth graders, but it's really it's sophisticated in terms of it's something that is used in advanced mathematics and also in science. But at its core, at its foundation, it's a very simple thing. And I'm talking about something known as vectors. A vector is a line segment of a certain length with a direction. It has a beginning and an end when we construct them, when we draw them. The beginning of a vector is a point, and then we indicate its end with an arrow. Now, these arrows do not mean it goes on forever. Sometimes in math, an arrow will indicate that you've got a line that goes on forever or a ray that goes on forever. But that's not the understanding here. This vector begins at this point and ends at the arrow, and this vector begins at that point and ends at that arrow. So what I want you to understand is the whole number 2 can be thought of as that vector right there that begins at 0 and ends at 2. And the significance of the arrow, if you're wondering, well, why is one end a point and the other an arrow, I'll just briefly mention, the reason we're not going to get into subtraction right now is negative numbers, and subtraction is connected with negative numbers, as we'll learn. Negative numbers have their beginning point at 0 and then an arrow pointing to the left, which is where the negative numbers are on the number line. These are both positive, so the arrow points to the right. And The way we add two numbers with vectors is we take the beginning point of one and put it at the end point of the other. So let me use a ruler here to kind of get a pretty good sense of the length of that vector right there. Looks like it's about 40 centimeters. That's how I made it a few minutes ago. So I'm just going to use that to guide me. What I'm going to do, I'm going to leave the two original vectors here. This one represents 2, and the one up above represents 4. I'm going to take the 4 and redraw it down here so that its beginning point is right on top of the end point of the 2. And that means that its end point now that it's been shifted, now that the 4 has been shifted down here to begin at 2, its end point is now right at 6. Now, actually, the two vectors, the 2 and the 4, really could be right on top of the number line. The 2 could be right here, and the 4 could be right here. See, with an arrow there, so there's the 2. And then the 4 is right on top of the 2, extending past it. So sort of lift the 4 up, move it so that its beginning point is at the 2, and its end point would be down here at the 6. By putting them up above, it's just a little bit easier to see. All right? Now, you've known for a long time that addition is commutative. So let's go back to the way this looked at the beginning, except let's do this. Let's take this 2, the 2 vector, and move it so that its beginning point is at the end point of the 4, all right? And then I'll use the ruler again. I think that's going to be 20 centimeters, yeah? 20 centimeters. So now, all right? So what I've done this time is I've started with the 4. I've taken the 4 vector, went from 0 to 4. It's really down here right on top of the number line. Okay? But to show it up there makes it more clear. Kind of gets a little bit hard to follow when everything's right on top of the number line. This time, we'll imagine the 4 being there, and we'll take the 2 and shift it so that its end point is its beginning point is at the end point of the 4, and then it's going to extend 2 more, so it's also going to land at 6. So what I just did is prove geometrically with these vectors that addition is commutative. Whether I started with the 4 and added the 2 onto the end of it, or started with the 2 and added the 4 onto the end of it, in both cases, of course, we end up right at 6. Now, this vector way of understanding addition is really more helpful. It's more important once we get to negative numbers. But if I lay the groundwork now, then it'll be there for us when we get to negative numbers much later in the year. Don't worry about negative numbers. There's no need to be intimidated by them. Like anything else in math, it'll come day by day, week by week. When you do your part of trying to understand the math as best you can and asking questions when you have difficulty, it'll all fall into place. I also thought we'd look at 3 plus 6 being 9. And of course, I'll do this not quite as neatly. I won't use the meter stick this time. But if we have a vector that starts at 0 and then ends at 3, that vector represents 3. And then, of course, we have another one that starts at 0 and ends at 6. And both of these vectors would really be right on top of the number line. So then we imagine picking this 3 up and moving it over here so that the beginning point of the 3 is now at the end point of the 6. Of course, it's going to extend the length of 3 units. Now it would be right on top of 9. Or if we started with the 3 and picked up the 6 vector and moved it so that the 6 vector's beginning point is right at the end point of the 3, and then of course it's going to reach 6 more units down. That's a terrible line there, but It's supposed to be a straight line. It's going to end up at 9 as well. So once again, the commutative property of addition, that might have just been something you took on faith when you were young, but now you can see there's a geometric interpretation of that. That's one cool thing about these vectors. All right, so what about fractions? What about if we have to add, add two fractions with different denominators? And I think I said before that I'm not going to show subtraction with vectors because that would involve left-pointing vectors, which are negative numbers. We'll do that later on. I can certainly show you how to do a subtraction where the two denominators are the same. All right, it's not mysterious. It's not hard. 5 sevenths minus 2 sevenths is 3 sevenths. So we'll just get subtraction out of the way. 19 elevenths minus 6 elevenths. It works just as well with improper fractions, by the way, ladies and gentlemen. There's no distinction in these formulas. The A could be bigger than the C, or the B bigger than the C. In other words, either one or both could be improper. 19 elevenths minus 6 elevenths is 13 elevenths. Notice the denominator stays the same and you simply subtract the numerators. Same for addition, except you add the numerators. Very simple. Never add or subtract the denominators. That's the key. So let's now look at some additions with vectors, like we did with these whole numbers down here. I'm going to leave that whole number line there for a moment because I'm going to come back at the end and look at this. I'll come back and look at that at the end. I wrote it there just to remind me. I hope I remember to look at it. And that'll sort of bring things full circle, and we'll close out this video, which can be very short because this is a very easy, straightforward thing to do, adding or subtracting two fractions with different denominators. What I've constructed up above is a fifths number line, starting at 0 and counting 1, 2, 3, 4, 5, and I'm right on top of the 1. So 5 fifths, 6 fifths, 7 fifths, 8 fifths, 9 fifths, 10 fifths on top of the 2, of course. We've seen this before. The 3 would be 15 fifths, and the 4 would be 20 fifths. And let's pick one first where the answer will be less than 1. Let's choose 2 fifths plus 2 fifths. Well, according to the formula, it's very simple. Keep the denominator the same, add the numerator, so this, of course, would be 4 fifths. Sometimes I like to say things like, I'll go through and ask a few people in the class, or maybe the same person, about 3 or 4 different questions. I'll say, what is 2 cookies plus 2 cookies? And very often, the student will simply say 4, but I will say 4 cookies. Right? 2 cookies plus 2 cookies is 4 cookies. So, and the student will say, oh yeah, of course. Then I'll say, well, what's 2 books plus 2 books? 4. Then sometimes the students get kind of stubborn. I'll say 4 books, and the student will say, yeah, 4 books. Okay. But see, that's important, because then I'll say 2 fifths plus 2 fifths. Well, it's 4 fifths. Right? It's kind of a similar concept of adding 2 of something and then another 2 of the same thing. And for our purposes, that same thing is the denominators being the same. So that's a sort of an intuitive way to realize that we don't add or subtract the denominators. When you add 2 cookies plus 2 cookies is 2 cookies, and 2 fifths plus 2 fifths is 4 fifths. Okay, that's pretty simple and straightforward. What does it look like in terms of vectors? I think to save time, again, I'm not going to use the rule book. 2/5 is a vector that starts at 0 and then it ends, its arrow is right at 2/5. And then we're adding another 2/5, so it's an identical vector. So we take one of them and sort of pick it up and shift it so that its beginning point is at the end point of the other one, and then there's the same length of 2/5. I'll erase that top one here, but here's 2/5, and here's another 2/5. It's just, imagine a copy of this 2/5 being picked up and shifted over so that it's point for point, end point to beginning point, and then of course it's going to, the sum is right on top of 4/5. It's not on top of 4 way down there, it's on top of 4/5. Now, you know, as young people, we often learn when we're adding that addition is movement along the number line, and these vectors are just a little bit more sophisticated way of looking at that, you know. To a young person, right, you start at 2, you're doing 2 plus 4 is 6, so you start at 2 and you count 4 more. 1, 2, 3, 4, and you're at 6. Well, it's very similar here. 2/5 plus 2/5, you start at 2/5, and then you add another 2/5, and so you count the fifths. 1/5, 2/5, 2 more fifths lands you at 4/5. Now, often when you're adding two fractions, even if both fractions are less than 1, they could result in a sum greater than 1, right? So this time, let's do 4/5 plus 3/5. All right? 4/5 plus 3/5. Now, looking at this formula up here, the A is 4, the B is 3, and each of these C's is 5. So there's the C, 5 and 5. The A is 4, the B is 3. What does the formula tell us to do? Add the A and the B, and then put that over C. Right? So it's 4 plus 3 over 5, or 7 over 5. And here's an example of how in math this happens so often, over and over again throughout your math lives. You learn different things, and sometimes within the same problem you have to put them together. So I've just talked about how we're going to add 4/5 and 3/5, and now we get an answer of 7/5. So we say, oh, I know that is the same as 1 and 2/5. So the teacher might want us to give 1 and 2/5 as the final answer to show that we know that 7/5 is the same as 1 and 2/5. And sometimes it's easier to understand the value of a number as a mixed number. Let's look at the vectors to indicate 4/5 plus 3/5. Well, 4/5 is a vector that begins at 0 and has its end point at 4/5. This is 4/5 right here. 1/5, 2/5, 3/5, 4/5. And then we have 3/5. Now 3/5 is also a vector that begins at 0, but it only reaches as far as the 3/5 here. Right? So it doesn't matter what order we do it in. Addition is commutative with fractions also. Right? Because whether you take this vector and move it down on top of the other, or you take this one and move it end to end with the other one, either way, the combined two vectors are going to reach to 7/5. Right? So let's take this one up top, move its beginning point to the end point. So we're taking the 3/5 and moving its beginning point right on top of the end point of the 4/5, and then of course it will extend 3/5 to the right. Right? So this here, this vector is the same as this one, it's just been moved. Let me get rid of that one for clarity. Right? So here's the 4/5 vector, it reached as far as 4/5. Here's the 3/5 vector, it originally reached only here to 3/5. Now it goes beyond the 4/5 and it ends up right here at 7/5. And clearly on this number line, the 7/5 is 2/5 past 1. Here's the whole number 1. 1/5, 2/5 past 1. 1 and 2/5. These are both correct answers. Sometimes we'll be asked to express the answer in its final form of 1 and 2/5. But 7/5 is not a wrong answer. So I said I wanted to come back down to whole numbers and just make, I just want to make this point. And at various points in math, even beyond like when you're doing high school algebra, it may be important and useful to recall that if you have a whole number, you can always put a 1 under it and not change its value. Whole numbers are fractions. You didn't realize it. So let's say you're back in first grade and you've never seen anything like this with a fraction bar. You've never seen 3/4. You might have heard of it, you might have heard of 1/2, but you've never been asked to work with something like this in first grade. But you were working with fractions, you just didn't realize it. These whole numbers are special kinds of fractions. Let's put it that way. And the easiest way to represent a whole number as a fraction, to make it look like a fraction, is to put a 1 under it. Okay? So what I have on the board here is 2 plus 4 equals 6, but in fraction form. Right? 2 over 1 plus 4 over 1 equals 6 over 1. Notice the same denominator, right? There's the c, the c, the c. I added the numerators, 2 and 4 to get 6. And then it's important to realize you can definitely simplify 6 over 1 down to 6. Now, why does this work? Why is 2 over 1 the same as 2? Well, let's look at this number line here. What does the denominator do? The denominator tells us how many equally sized pieces do we divide the unit into, the distance between 0 and 1. Well, this number line right here, as is, the original number line, is a number line with the unit being divided into just one piece. There it is. There's the one piece from 0 to 1. There's the one piece from 1 to 2. There's the one piece from 2 to 3. It might seem a little silly, but it's a good way to realize that these whole numbers that we're so familiar with really are fractions. And so I didn't put any dividing points between 0 and 1. I just wanted one piece. I wanted the unit to be divided into one piece. So there's nothing to do, right? Now, maybe I should point this out. All right, so, as far as, fraction, there's 2 over 1. Why is it 2 over 1? Because the unit is one piece. It's been divided into one piece, not really divided at all, just one piece. And then 4 over 1 is this one. 1, 2, 3, 4. And that vector is 4 over 1, so you end up with the 6. Right? So I'm just trying to show that down here is really, up here with the fifths is really not any different than this. As young people, we were working with a once number line where the denominator was 1. We didn't, nobody looks at it that way in first grade, but now we can. Yeah? And now that we have a fifths number line, we just, the movement along the number line, the young person, for 2 plus 4 equals 6, starts at 2, counts 4 more to get to 6. We start, up here we started at 4 fifths, and then we counted 3 more fifths to get to the 7 fifths. It's a very natural extension of the addition of whole numbers. So, I think that, one last thing. Yeah, I said the easiest way to represent a whole number as a fraction was to put a 1 under it. But there are actually an infinite number of ways of representing any fraction. This kind of gets into a video we'll have very soon about the topic of equal or equivalent fractions. But for right now, let me just make this point. Let's look at this whole number 2. I suggested that you could think of it as 2 over 1. Right? 2 over 1. Because the unit is one piece. It really hasn't been divided. It's been divided into one piece that's really not divided. All right. So here's 2 over 1. But how about this? 6 over 3. Now I've told you that we can think of a fraction as a division, read from top to bottom. 2 divided by 1 is 2. And 6 divided by 3, also 2, right? But why does that work? Why is it 6 over 3? So let me come back up here. This was the whole number line. Up until now, I haven't made it into a fraction number line. But what if I do this? What if I put a point here, a point here, a point here, and a point here? Well, now I have a thirds number line. 1, 2, 3/3 lands us at 1. And then 4/3, 5/3, 6/3 lands us at 2. And I could do this for any number of, in the denominator. You know, this would be the same as, multiply the top and bottom here by 4 and get 8/4. 8 divided by 4 is also 2, right? So all of these equal 2. And to show this as a fourth number line, right, to show that the whole number 2 is also 8/4, what I have to do is make a fourth number line, right? And I did that sort of a quick sketch here. It may not be perfect, but 1/4, 2/4, 3/4, 4/4, right on top of 1. And then 5/4, 6/4, 7/4, 8/4 lands me right on top of 2. So that's a little extra nugget. But basically, adding and subtracting two fractions with different denominators with the same denominator is very simple. And you will be ready to add and subtract fractions with different denominators as we go forward step by step. Let's close with a couple of quick examples. You can do them yourself, and I'll put the answer in there that I got, and I'm sure that we're going to agree. All right, so how about 9/20 plus 17/20? What about that? Try to picture a 20th number line. Start at 9/20 and go 17 more 20ths. Where are you going to be? What's 9 cookies plus 17 cookies? 27 cookies. 9/20 plus 17/20 is 26/20. Now, we're going to have something to say about that in the future. Give you a little preview. We might be comfortable right now that that's 1 6/20, right? Because this is what I was saying before about improper fraction to mixed number. We've already sort of assumed that we could add fractions when we took something like 26/20 and thought of it as 20/20 plus 6/20. 20/20 plus 6/20 is 26/20. Why did I just do that? Because that 20/20 is 1 plus 6 more 20s, so we have that mixed number. And then this next thing that I'm going to show you, we're really not ready for. One of the next videos, very soon, is going to be talking about the equivalent fraction. We're going to learn, you don't already know, that 1 6/20 is exactly the same as 1 3/10. 6/20 equals 3/10. And if you don't understand that right now, don't worry. That's a big topic that we will cover soon. All three of these numbers are the same. They're all the same point on the number line. 26/20, 1 6/20, 1 3/10. All the same number. Those points are right on top of each other. The point representing each of these is really the same point on the number. Well, how about this, ladies and gentlemen? How about, let's make it really interesting. How about if we do, 31/40 minus 17/40. When we add or subtract fractions, we never add or subtract the denominators. So the denominator here is 40. And now this is the subtraction, so we have to do numerator minus numerator. Up here, this formula, A over C minus B over C. Denominator stays the same, C. And then, because we're subtracting the fractions, we just subtract the numerators. And of course, you should do this mentally by now, right? You don't have to do this on paper. It's 14. right? 14/40. Oh my goodness. Didn't know this was going to happen. That's actually equal to 7/20. See if you can look at the 6/20 and being equal to 3/10. The 14/40 being equal to 7/20, and see if you can figure out on your own a little bit of what's going on when we have the so-called equal, equivalent, or equal fractions that we're going to look at later. So, ladies and gentlemen, a little over 30 minutes. Not bad. Adding and subtracting fractions with the same denominator is very simple. Make sure you own it now. Nice to see you again. Take care.